Hello everyone, welcome to the control systems. This is lecture 7 on transient and steady state response analysis. Here is the outline of the lectures, and this lecture is based on the textbook on modern control engineering by Katsuhiko Ogata and chapter 5. So I recommend you to read this chapter first before starting this lecture, or you can just go through these lectures and then get back to this chapter after completing these lectures. Okay, so we'll begin with the introductions, and the first step in analyzing a control system was to derive mathematical models. Okay, and once such mathematical model is obtained, various methods are available for analysis of the system performance. Okay, and there is something that you need to do before we go further. For example, we want to check the performance of the system. We want to study the behavior of the system, and there are commonly used test signal that we can use in order to study the behavior of the system. For example, step functions, ramp functions, impulse functions, acceleration functions, sinusoidal functions, and phase noise. Okay. So if the input to the control system are gradually changing functions of time, and then this ramp function uh, is a good candidate for testing. And similarly, if the system is subject to the sudden disturbance, and this step functions of time may be a good test signal. Okay. Uh, on the other hand, if uh, the system subjected to the shock input, so an impulse functions may be the best. Okay, when the control system is designed on the basis of test signals, the performance of the system is respond to the actual input is gradually satisfactory. So with this test signals, mathematical and experimental analysis of the control system can be carried out easily. Okay? Since the signal are very simple functions of time, and note that we will use the signal marked blue, basically just a step function, ramp function, and impulse function in these lectures. Okay, let's move to the next section, next slide. We'll consider transient response and steady state analysis. So for the LTI system, the time response of the control system consists of two parts: transient response from initial state to the final state, and steady state response when time approach infinities. Okay, and the system response CT can then be written like this: is the sum of the transient response and the steady state response. Okay? So in order to design any controller or do analysis, we need to have the knowledge of the components. For example, we need to know what kinds of sensor to be used. We need to know the dynamic behavior of the plant, or the dynamic behavior of the system, what kinds of actuator we should use in the system. And from that, we'll understand the behavior of the system, the dynamic behavior of the system. Okay? And then an important question to ask before we do anything is the stability. So whether the system is stable or unstable. Okay? So there is something that we need to know. For example, a control system is in equilibrium if in the absence of any disturbance or input, the output stay at the same place, same state. Basically, there is no effect from outside world. Okay, and then another thing that we need to know is an LTI system is stable if the output eventually come back to its equilibrium state when the system is subjected to the initial condition. Okay? For example, this kinds of system, you inject the signal, and at a period of time, it will come back to its initial state. So an LTI system, this is not LIT, it's LTI, is critically stable if oscillation of the output continue for hours. And it is unstable if the output diverge without bound from its equilibrium state when the system is subjected to the initial conditions. And an important system behavior other than absolute stability to which we must give careful consideration include relative stability and steady state errors. Okay? So since the physical control system involve energy storage and the output of the system when subject to the input cannot follow the input immediately. So it have some transient response, okay, some oscillation or overshoot sometime. And the output of the system at steady state does not exactly agree with the input in many cases. So the system is said to have the steady state errors. And this error is the indicative of the accuracy of the system. So we have transient response and steady state response. And we also have the steady state errors. Okay. Finally, when time go to infinity, uh, the signal cannot follow the reference signal 100%. Okay, so it exhibits the steady state errors.